Hello, everyone. My name is Sahil, and today I'll be talking about some profit inequalities with linear correlations and augmentations. So I'm currently a postdoc jointly between Princeton University and Institute for Advanced Study. This is joint work with Nicole Imolica from Microsoft Research and Bo Wagner from University of Colorado. So let's start out with a motivating example. So suppose you want to buy a house. So you are a buyer in the houses in the market, and these house values are being revealed to you one by one. So maybe for some reason you discarded the first two houses, and now the third house, its value xi is being revealed to you. You have to immediately and irrevocably decide whether you're purchasing this house, which basically means that, okay, if you buy this house, then you get the value xi and the game ends. You're not allowed to buy any more house. On the other hand, if you discard the house, then you cannot purchase this house later. So it's an online problem. The challenge comes because you want to select the highest value house. And because you don't know the values of the houses, it's difficult for you to decide the highest value. And these house values could also be correlated because of some common features, maybe because of their location or something else. Okay, so what are the high-level results of our work? So what's known is that in general, if these house values are independent, then there are some threshold-based algorithms that really work well. For example, in the extreme case, if you knew all the values of the houses, then you could just set a threshold of the highest valued house and just purchase that one. So that was awesome. But in general, what we show is that if there are correlations, these threshold-based algorithms don't work. Instead, what you have to do is somehow remove some of these houses, like somehow randomly winnow some of these options and then run a threshold algorithm. And those algorithms work pretty well. The general threshold algorithms are not. Let's first start by recalling how to handle the independent value case, the case that I'm saying where threshold algorithms work well. So this is actually the same as the classical profit inequality problem, where these values of these houses, so the ith value house xi is drawn from some known distribution fi. Your goal is to maximize the value of the house that you get, the reward. And what you're comparing yourself is to the value of the highest house or the highest item, as I would say, chosen in hindsight. The question is, what fraction of it do you get, your expected value? And what's known as these threshold algorithms, which basically just select the first value, which is above some value, they give you a very good value, approximation factor. So you can get an approximation factor of 2 by setting a threshold either of the mean, which is the expected max over 2, or you can set the median threshold. Both of them are known to give you a tight approximation of 2, tight in the sense that there's no alternate algorithm that actually can do even better than 2. So they are not only giving you a good guarantee, but also the optimal guarantee. And these results have been also extended beyond single items, like what happens if you select R items. So it turns out that the problem becomes easier and your approximation ratio starts tending towards 1. And for matroids, it's known to be like the tight approximation ratio is 2. Good. So these are all in the independent setting. And we want to study correlations. Unfortunately, in the most general setting of correlations, Hill and Kurtz already showed that you cannot do much. Basically, omega n is approximation ratio is the best you can get, which is pretty much equivalent to selecting one of these items at random. So, okay, but we want to handle correlations. So what the route we want to take is what happens if the correlations are relatively structured or they're relatively mild? What can we do in those cases? Can we handle somehow correlations in these online models? The model that we study is the linear correlation model, which was originally introduced by Bateni et al. And it was inspired by a work of Chawla, Malik, and Sivan on common base value models, where the setup is you have these n values of these n houses, which are being revealed to you one by one for n items. They could be correlated, but there are some underlying features, y1 to ym, which are basically affecting the values of these items. So the values of these features are drawn independently from some known distributions, and they're affecting the values of your houses via in a linear way, via some linear matrix. So a matrix where the Aij entry basically denotes how much item i's value is affected by feature j. So to repeat it a bit more formally, what I'm saying is that, okay, you have this vector x, which denotes the values of these items or houses. It's affected linearly by this feature vector y. The values of these y's are drawn from some known distributions, but you never get to see the outcome y's. You only get to see outcomes x's. So you're getting indirect ways of seeing the outcomes of these y's, but never directly. And this matrix A is known to you. So in the extreme case where A is the identity matrix, then it becomes just the profit inequality model because xi equals yi, and you get to see it. The question is, can you still get a constant approximation? And so it turns out actually what we'll show is that constant approximations are not possible And your approximation guarantees depend on the sparsity of this matrix A. The important parameters are the row and the column sparsity. For example, the row sparsity denotes how many features affect the value of it. So as I was saying, like, what our main results are that actually the tight approximation ratio turns out to be the minimum of the column and the row sparsity. So as long as at least one of your row or the column sparsity is small, say a constant, then you can get a constant approximation ratio, but not in general if both these ratios are these sparsities are large. And threshold algorithms perform very bad, so you need to really do something else. Simple threshold algorithms don't work fine. And so what we show is that also in the multiple items case, you can actually get approximation ratios where when the number of items you're selecting is much more than the column sparsity, then this ratio turns out to be approaching 1. On the other hand, when the number of items is much more than the row sparsity, somehow you cannot actually get any improvement. So this is basically, there's a difference between the row and the column sparsity in these settings. And the main ideas are, okay, although the threshold algorithms don't work, what you can run is some inclusion threshold algorithms, which basically means you can randomly discard some subset of the items and then run a threshold algorithms on them. And one of the lemmas, which I'll talk about, is this augmentation lemma, which is some kind of a robustness result, where you want to say, like, even if I add some positive nodes, then your value does not go down. Okay, so the outline for the talk is I've just introduced you this model, the linear correlations model. Now I'll talk about the threshold algorithms and the augmentation problem, and then I'll conclude with some proof ideas. So let's first have a quick look at why threshold algorithms perform bad. So what I'm saying is that there are instances where if you set any threshold, basically the best you can get is an omega n approximation, which is much worse than a constant approximation. And this holds even when the row and the column sparsity are very small, like even just 2. And here's the quick idea of the instance. So imagine xi, the value of the ith item, ith house, depends on just features I and I plus 1. It depends a lot on feature I, but very mildly on feature I plus 1. So as you can see, like this dependency can be denoted in a matrix, which has only 2 column sparsity and row sparsity. The distribution of yj's are given here, where it takes a very large value with some very small probability. Turns out some simple calculations show that the optimal here is going to be omega n, because in expectation, the y's could be large. There are many of them. However, any threshold-based algorithm that you design, if you set it like, say, close to n to the j, the best you can get is roughly a constant. Somehow it's a simple calculation, but it basically shows that any threshold algorithm can perform only well for when yj is active. It's giving n to the j value, but that happens only with a small probability. So in expectation, you only get a constant value. Okay, so in case you got lost, the point is that threshold algorithms naively don't work well when you have correlations, even in these special kinds of linear correlations. So instead, the main idea that we got from those instances was this following augmentation problem. So the idea of the augmentation problem is the following, that, okay, in general, correlations are hard to handle, but what if I have a special kind of a correlation where you have each item I takes value, which is sum of 2 components. One is some independent component, which is basically something similar to like the profit inequality, plus you have some positive noise. So this is something which could be correlated with other things, other values, but it's only positive. The intuition you want to keep in mind is that, okay, if I give you this profit problem or like any of these online problems, if somehow somebody increases the value of all these variables, you would expect ideally that the value only increases because the values of these houses and items are only increasing. Can you actually prove this formally? Are there algorithms? So this augmentation problem is basically saying the same thing, that, okay, if you have some independent problem of these zi's, if I add some positive noise, can you still guarantee me an algorithm which gets you expected max of the zi's, the independent part? And if the noise was this 0, then it's just a profit inequality problem. So here's a simple example which shows that actually the median threshold algorithm, so if you have independent distributions that both of them, median and mean thresholds, as we were saying, will give you a constant approximations. However, if I add a slight noise, then the median threshold algorithm turns out no longer works fine. It actually gives you a very bad approximation guarantee, whereas mean threshold algorithm continues to give you a constant approximation. And is that a coincidence or something special? And what we actually show is that actually this augmentation lemma, that mean threshold algorithms are always robust to such augmentations. So our augmentation lemma basically says that if you set a threshold of expected max over 2, you can always get a value in expectation, which is half of the expected max Di. So the independent component, you're getting at least a constant approximation of that. And this is going to be our main subroutine that we are going to exploit. So now I'll quickly give you some ideas about our proofs. So first, the column sparsity case. Remember, in the column sparsity, like the row could be large, but each column is, say, a constant sparsity. And here our high-level idea in this inclusion threshold algorithm, inclusion threshold mechanism, is to ignore each xi, like the next item, with a decently large probability, say 1 minus 1 over scol. So only with some, but scol is a constant, so it's still some constant probability you're considering this variable, this item. And then you, whenever you get, you assign each of these features to the first surviving xi. And the point that you exploit is, because column sparsity is small, each feature only belongs to a small number of xi's. So there's a decent chance that whichever is the right xi that you should be targeting, that contains the yj corresponding to it gets assigned to it. And basically, this allows you to apply the augmentation lemma. So I'm not covering the details, but it's not super hard. You can find it in the paper and get this order scol, order column sparsity approximation ratio. And you can also get a similar approximation ratio in terms of column in the row sparsity. However, you have to be a little more clever about how you're discarding these elements. So in particular, you need to construct some dependency graph and create a correlated distribution according to which you are discarding these boxes. But it's still some inclusion threshold mechanism that works fine. And for multiple items, also we approve our results. But the idea is basically to extend this augmentation lemma, the mean-based augmentation lemma, beyond a single item and get some tight approximation ratios. So here are some conclusions. One of the open questions is, okay, one is to get these tight approximation ratios. So we are not fully tight in terms of the exact constants. And the other thing is can we extend this to matrix constraints? Thank you.